Hi everyone, welcome to Cola Teaches Math. So today we're going to do a review on Unit 1, Limits and Continuity. So first let's chat about what topics you need to know for the AP exam from Unit 1. So you can see right here, I have a bunch of topics listed. These are just like the main topics, how I group them in my class. Limits from graphs, limits using algebra, trig limits, one-sided limits, infinity limits, continuity, and the IVT. So let's go through each one and see how I teach it and get you prepared for Unit 1. Okay, excuse me. So, Section 1, limits from graphs. So I have this graph right here, and what we're going to do is we're going to go ahead and evaluate the following limits right here from the graph. Okay, so it seems kind of silly, but look, if I'm making a number line and I have 3 in the middle, this little symbol right here means we're approaching 3 from the left. So we're literally approaching, to the left of 3 on the number line. So what number is that? Is 2. So if we're approaching 3 from the left, we're going to look at this part of the graph, 3 from the left. This is the left of 3. What is the y value that we hit? We hit a y value of 2. So this is going to be 2. Next, we're going to approach 3 from the right. So 3 from the right is in this direction. So if we look at the graph here, 3 from the right, what is the y value that this graph is approaching? It's approaching a y value of 2 also. Great. So now because the limit from the left and the limit from the right equal each other, then the entire limit is going to be 2. So big takeaway here is the limits can exist at holes. They're going to try and test us on that somewhere. So limits can exist at holes. And last but not least, we want to find f of 3. So f of 3 is saying when x is equal to 3, what is y? If you come over here and you look at the graph, it's this point right here. So when x is 3, we are filled in right here, and that's going to be equal to 5. All right, second row. So now we're going to approach, this is saying the limit as we approach 6 from the left. Okay, so 6 from the left, here is 6 right here. The left of it is this piece of the graph that I'm highlighting in pink. What is the y value that I'm reaching? And it is going to be 5. 6 from the right, I'll do it in blue. We're going to the right of 6. What is that y value that we're reaching? It is 2. Oh, look at that. They do not match. 1 is 5. The limit at the right of 6 is 2. Because they don't match, then the entire limit's going to be d and e. Because remember the main idea, the limit as we approach some number from the right has to equal the limit as we approach that number from the left in order for the limit to exist. And last but not least, let's find f of 6. So I closed it in right there. F of 6 is going to be 3. So that's how you're going to evaluate limits in the graph. Big idea, limits can exist at holes. All right, next topic. Limits using algebra. All right, step 1. You're always going to want to plug in first. Meaning, you're going to take whatever we're approaching, in this case 5. We're going to replace all of my x's with 5. See what I get. This one we're approaching, x is approaching 0. Replace all of my x's with 0. See what I get. Maybe it'll work out and you'll get a number, but it probably won't. You're most likely, not always, going to get 0 over 0. That is called indeterminate form. And if you get 0 over 0, you have 2 options. Option 1, if there's no square root. So these 2 examples have no square root. Then we are going to factor, cancel like factors, and then plug in again. So you're going to watch me do that here. Because if you plug in 5 right now for x, you're going to get 0 over 0, indeterminate form. So we're going to factor. So factor the top with dots. Cross out the like terms. And then you're just going to plug into what's left. So what's left is x plus 5. We are going to replace x with 5 because that's what x is approaching. And if I go ahead and do that, if I replace x with 5, we're going to get a limit of 10. Now, what is happening right here? See these like factors that I crossed out? When the factors cross out, so if the factors cross out, that means there is a hole on the graph. So that means there is a hole. And how do I know where the hole is? You take the factor that we crossed out. You set it equal to 0. So in this first example right here, there's a hole at x equals 5. And the y value is the limit that we just got. So at 510, there is a hole. Okay? Which we'll go over what that means in a minute. All right, next example. If we replace x with 2, you're going to get 0 over 0. So now we're going to factor. We're going to factor the top. So one factor is going to be x minus 2. The other factor is going to be x plus 1 over x minus 2. Cross out the like terms. So that means that there's going to be a hole at x equals 2 because you're setting the factor equal to 0. And now what we're going to do is we're going to take what's left and we're going to replace x with 2. If I replace x with 2, we are going to get a limit of 3. So that means the hole is at the point 2, 3. All right, next example. What happens if there is if there is a square root? In the limit question, when you plug in, you get 0 over 0. You're like, what do I do next? Oh, there's a square root. So that means we're going to multiply by the conjugate. All right, so let's go through this. I do need a little bit more room, so we're going to move this guy down here and go back up there. All right, so when we multiply by the conjugate, you're going to keep the square roots the same. You're just going to change the sign in between. So if this was a minus, now it's going to become a plus sign. So here is my conjugate. Okay. Step 1, you're going to multiply the top times the top. Okay, we're going to simplify it. And the trick is you're going to take the first term times the first term. So watch, that's going to give me rad 2 times rad 2 is 2. Negative times a positive is negative. And then you're going to multiply the second term times the second term. It's the quickest way to do it. Make sure you put this in parentheses because we're going to need to carry that negative through. And then what you're going to do on the bottom is you're going to just place them next to each other. So we're going to have x times the conjugate, rad 2 plus rad 2 minus x. Simplify the top. So if I put the negative through, the 2's are going to cancel, and the double negative is going to make a positive. Now you're going to simplify. You're going to cross out. Something's going to cross out. If nothing crosses out, you made a mistake. You got to go back and find it. So the x's are going to cross out, and there's still going to be a 1 on top. So when I rewrite this, because I'm going to take the limit again, I'm taking the limit as x approaches 0 of my simplified form. So my simplified form is 1 over rad 2 plus rad 2 minus x. So now if I take a second and I replace x with 0, you can see you're going to get 1 over rad 2 plus rad 2, which is 1 over 2 rad 2. You only have to rationalize it if it's a multiple choice question and if they chose to rationalize it. Okay? All right, next example. Here's another conjugate. If you replace x with 3, you're going to get 0 over 0. So we're going to multiply by the conjugate. So the conjugate is rad x plus rad 3 over rad x plus rad 3. You're going to do my trick. You're going to do first term times first term. So that's going to give me x minus second term times second term, 3. All over the denominator, we're just placing the denominator next to each other. So you can see that I'm doing that here. And you can see now the x minus 3 and the x minus 3 cancel. All right, what am I left with? We're left with the limit as x approaches 3, 1 over the denominator, rad x plus rad 3. We're going to replace x with 3, and you're going to get 1 over rad 3 plus rad 3, which is 1 over 2 rad 3. Done. Okay, so that's using algebra. Your options usually are factor or multiply by the conjugate. All right, let's go through some trig limits. So for trig limits, you're going to want to memorize these right here. I have the 3 rules up top. So as long as x is approaching 0, that's the biggest thing. You're able to say that all of these are equal to a over b. And these rules only work for sine and tangent, not cosine. And the trick is x must be approaching 0, nothing else. So let's put the rule in action here. So we have sine 2x over sine 3x. X is approaching 0. So it's just going to be the ratio of the coefficients in front of the x, 2/3. All right, next example. I got a few tricky ones here. These are fun. So I said the rules work for tangent as well. But now you notice how you have tan squared x. So what I like to teach my kids in my class is I say, okay, break this up. So we're going to break it up to be tan x, because that's tan squared x, over x over x. You could just do one big line if you want to. And the reason I did that is because it's x squared. Now, look here. This goes to 1, this goes to 1. Because I said the rules apply for tangent as well. And this is the rule right here. Sine ax over bx is a over b. So tan 1x over 1x is 1 over 1, which is 1. 1 times 1 equals 1. I'm going to apply that same trick for this next example. You're going to split the sign up, so it's going to be sine x. But notice how there's only one x. So I'm going to only give it to one of them. So what I like to teach in my class is I say, oh, find your best friend. So when I say find your best friend, I'm going to take one of these rules, and you're going to see if you can find it in the question. So here's my best friend. Sine x over x goes to 1. So now what am I left with? I'm left with 1 sine x. Now I'm going to take what's left and replace x with 0. So if I do that, you're going to have 1 times sine of 0. You have to know that the sine of 0 is 0. So 1 times 0 gives me 0. All right, next one. This one I'm going to manipulate it a little bit. I can see that I have a tangent, so I'm going to take this cotan 5x and I'm going to turn it into 1 over tan 5x. Because cotangent is 1 over tangent. So cotan 5x is equivalent to 1 over tan 5x. So now I'm going to find my best friend. Here is my best friend right here. Tan 4x over tan 5x is just going to be 4/5. Because you're just going to take the ratio a over b. Because these rules up here work for tangent as well. All right, next, one-sided limits. So this is going to be in the non-calculator section, so you have to understand the reasoning here. So I have a number line here. I have 3 in the middle because I'm asking you to approach 3 from the left, 3 from the right, and then just 3. So if I'm approaching 3 from the left, we want to get really, really close to 3. So let's say we want to get to 2.999 minus 3. So now you got to say to yourself, okay, is this bottom number going to be positive or negative? And that's going to be 1 over a super small negative number. 1 over a super small negative number. Like if you had a calculator right now, you can do 1 over negative 0.01, 1 over negative 0.001. And you can see that if you actually evaluated those fractions in your calculator, your answer is going to get bigger and more negative. So 1 over a super small negative number is going to be negative infinity. So that's just something that I taught my kids to memorize. And now over here, 3 from the right, let's do 3.01. Because all you guys want to see is if this number on the bottom is positive or negative. Okay? So this is going to be 1 over a small positive number, which is going to be positive infinity. Now, the whole idea of limits is in order for the limit to exist at an integer, the limit from the left and the right have to be the same. Well, the limit from the left is negative infinity. The limit from the right is positive infinity. So the limit as x approaches 3 is d and e because they don't match. So that's what you need to know for one-sided limits. That's what I'm highlighting here in blue. And you have to be able to do them from a graph, which I did before. All right, infinity limit rules. Here we go. So if the highest power on top is greater than the highest power on the bottom, then your answer is your limit's going to go to infinity. Okay? So what I would do, no, let's not even do that yet, is I taught my kids find the highest power, circle it. So that's the highest power on top. That's the highest power on the bottom. And now you just need to make sure that both terms, you got to pay attention to the coefficients in front. So both coefficients are positive, 1x to the fourth and 1x. And we're approaching positive infinity. So then this is going to go to infinity. What I do like to teach my kids is I like to teach them to think we're approaching infinity. So the top is going to be infinity to the fourth over infinity. To try and figure out if this is positive or negative infinity, you have to look and see if the answer, like infinity to the fourth, a positive number over a positive infinity is a positive. I'll give you an example on when this would go to negative infinity. So watch. I'm just going to change this. So let's say limit as x approaches infinity of negative x to the fourth plus 2 over x minus 4. So same thing, circle the highest power on top and bottom. But because this leading term right here has a negative 1 in front, this is going to go to negative infinity. And the way I taught my kids, if you really want like a concrete way to do it, is you're going to take x and replace it with infinity, the highest power. So I'm taking negative x to the fourth, and then I'm going to replace x down here with infinity. If you actually think to yourself, infinity to the fourth is a positive number times a negative is going to be negative. And then the bottom is positive. A negative divided by a positive is negative, which is why this is going to go to negative infinity. You really only need to do that reasoning out from if the power is higher on top. Okay, so now if the highest power on top equals the highest power on the bottom, so find the highest power here and here, all you're going to do is take a ratio of the coefficients. So that's just going to be 4/3, 4 divided by 3. Done. And last but not least, if the highest power on top is less than the highest power on the bottom, so circle the highest power here and here, then that's going to go to 0. Okay? All right, so let's look at this first example. So highest power on top is here. Highest power down here is here. Let's do my analysis. So you're going to have negative 2, negative infinity cubed over negative infinity. So reason this out with me. A negative cubed is still going to be a negative number. Times a negative number means the numerator is going to be positive. The denominator is negative because it's negative infinity. A positive divided by a negative is going to be negative infinity. So this is going to go to negative infinity. And now this next example, circle the highest power on top, circle the highest power on the bottom. Now guys, the highest power is under a square root. So the highest power on top is going to be radical x to the fourth, which is going to be x squared. Divide the exponent by 2. And the highest power on the bottom, if I actually take the square root of everything, square root of 3 is rad 3. And now you're square rooting x to the fourth, it's x squared. So the highest power on the bottom is x squared rad 3. Do you see now how the powers match, x squared and x squared? So you're going to take the ratio of the coefficients. That's a 1, and then that's going to be rad 3. Done. All right, number 6, continuity. I love a good continuity question. So let's chat about when we are not continuous first. We are not continuous at wholes, which are known as removable discontinuity. So it's going to be a picture like right here. And we talked about finding the whole by looking at the like factors and then cross out. We're not continuous at a vertical asymptote. That's called non-removable. Guys, I need you to think of continuity as, can I draw my picture without picking up my pencil? Draw a picture without picking up pencil. And last but not least, a jump discontinuity looks something like this. That's like when you have a big gap on the graph. So now you need to be able to tell if a rational function is continuous versus a piecewise function. So a rational function, here we go. We're looking to see, so step 1, you want to always look for the whole first. then the vertical asymptote. I'm going to abbreviate vertical asymptote VA. Okay, so how are we going to look for the whole first? We're going to factor. So the top does not factor. The bottom factors. Cross off the like factors. That means there's a hole there. There's a hole when that factor equals 0. So x equals 5. There is a hole. There's a removable discontinuity at x equals 5. Then you're going to look at what's left. Okay, what's left? 1 over, so this is the simplified function, 1 over x plus 5. Then you're going to look to see when there's a vertical asymptote. So a vertical asymptote is where the function is undefined. Well, fractions are undefined when the denominator equals 0. So if you set the denominator equal to 0, at x equals -5, we're going to have a vertical asymptote, also known as a non-removable discontinuity. So you always want to look for the whole first by factoring, and then the vertical asymptote. Okay, so remember, whole is when you have like factors cancel, and the vertical asymptote is where the function's undefined. So for fractions, it's when the denominator equals 0. All right, next. Piecewise functions. Okay, so for piecewise functions, there's a lot of rules that you guys need to show. Not a lot, not a ton. I'm going to write them right up here so I have some space. So for this particular question, I want to figure out if we're continuous at x equals 2, because that's where the piecewise function is split up over. So I'm going to evaluate f of 2. You're going to use the one with the equal sign. If I take this top piece and replace x with 2, you're going to get this. You could do this in your head, or you can show it. You're going to get -2. Okay, step 2. You need to show that the limit exists as we approach a. Well, in order for a limit to exist, we need to figure out the limit from the left and the right. They have to be the same. Okay, so let's do that. If I'm approaching 2 from the left, guys, we're going to be using this top piece. 2 from the left means number smaller than 2. This represents number smaller than 2. So this little symbol here that I'm going to highlight in pink just helps you choose which piece to use. I'm using this top piece. Then you're ignoring that symbol and you're plugging the integer in. So if I plug 2 in for x, we are going to get -2 again. Same thing. 2 from the right means we're going to use this bottom piece of the piecewise function. The limit of a number is just the number. So the limit of -2 is -2. So the limit exists. I'm going to put a little check mark because the limit from the left and the right are both -2. And then your final step is your function value from step 1 has to equal the limit value from step 2. Okay, so the function value from step 1 has to equal the limit. So what do we get? The function from step 1 equals the limit we got in step 2. So you have to make your conclusion. I'll write it in a different color so it stands out. You have to say f of 2 equals the limit as x approaches 2. All right, and last but not least, oops, I forgot. There. Find the value of a to make the following continuous. I love these questions. So in order to be continuous, guys, the function has to exist. So step 1, f of 3 has to exist. Well, f of 3, if we plug x equals 3 in, because f of 3, you're going to get 3a plus 1. So guys, you don't really need to show that. I kind of want you to know how to do these questions. If they say find the value of a to make it continuous, all you're literally doing is setting the top piece equal to the bottom piece. That's what I need you guys to know. So I'm going to take the top piece, ax plus 1, and I'm setting it equal to the bottom piece because I need the limit from the left to equal the limit from the right. And I'm going to replace x with 3. That's it. So let's replace x with 3. That's 3a plus 1. equals 9a minus 1. And now you're just going to solve for a. So you're taking the left-hand limit and setting it equal to the right-hand limit. So if we go ahead and do that, you're going to get 2 is equal to 6a, divide by 6. That means when a is 1/3, this piecewise function is going to be continuous. And now this one's a little weird down here. It's not, like, it's an interesting piecewise function. So there's no inequality. We have a function that says x can't be equal to 2, but when x is 2, the y value is a. So for this one, I'm going to apply the continuity rule. So step 1, we need to figure out what f of 2 is. Well, when x is 2, they're telling us it's equal to a. Great. Step 2, I need to make sure the limit as we approach 2 exists. Well, look at this. If we replace x with 2 right now, you're going to get 0 over 0, which is bad. So if you go back to my first few slides, when you get 0 over 0 and there's a square root, we're going to multiply by the conjugate. So let's multiply by the conjugate. I'll do it in a different color. 2x plus 5 plus rad x plus 7 over rad 2x plus 5 plus rad x plus 7. Okay, first thing, multiply the first 2 together, which means you're just going to drop the radical. So 2x plus 5 minus, multiply the next 2 together, drop the radical, x plus 7. And then on the bottom, you're just going to place them next to each other because something should cancel. Let's simplify the top. If I simplify the top and pull that negative through, you're going to get x minus 2. All over the same bottom. Ooh, I can't really fit it. I can't fit it, so I'm just going to write it like that. So the x minus 2's cancel. Okay, and now we're going to plug into what's left. So I'm going to take the limit as x approaches 2 of 1 over the radical, 2x plus 5 plus rad x plus 7. Replace x with 2. Okay, so what do we get? We're going to get 1 over, if I replace x with 2, that's going to be 3 plus 3, which is going to be 1/6. So in order to be continuous, the function value, right here, has to equal the limit value, which means a has to be 1/6. And last but not least, the IVT, which I think is a very straightforward theorem. It's just kind of annoying on how to explain yourself. So basically it's saying if f is continuous, that's like the main idea, we have to be continuous, on the closed interval 2 to 8. So here's 2, here's 8. They want to know, will there be a value of c, so x, where y is going to equal 5? So this is basically saying, am I going to hit a y value of 5? Well, if I am continuous and I connect these purple dots, I can connect them in a multitude of ways. I can make it a straight line, which obviously we're going to hit a y value of 5 right here. I can go like this. We hit a y value of 5 right there. I can go under. We hit a y value of 5. I can make it totally squiggle, and I can hit a bunch of y values of 5. Because we're continuous, of course we're going to hit a y value of 5. So how do we write it out? So we're going to want to say, since f of x is continuous, and this is where I tell my kids, list the coordinates. So we're going to say f of 2 equals 3, and f of 8 equals 7. And then I like to say, because 5 is in between these y values, so 5 is in between 3 and 7. And every teacher's different, but you do want to say that in some sort of words. I like to write like an inequality. By the IVT, then you're going to repeat the question. F of c equals 5 for some c on the interval 2 to 8. And that is it for Unit 1.